and told you were going to be worrying and thinking about it all weekend, which I'm sure you were. So here we have a product that I want you to get from, among any other reagents, this alkyl halide starting material. And I'll give you a hint to get started. You can use lithium metal to convert that, or magnesium metal if you want, to convert that into an organolithium reagent or a Grignard reagent. Now, how do you think I could have made this? Start by looking at that product. What bond would I have to have made if I want to start with this? Go ahead, take a risk. I won't laugh, I promise. No, nobody wants to because I said I might laugh. Okay, go ahead. Say that again. Is there supposed to be a double bond somewhere because it's attacking the beta carbon? Good. You've noticed that this benzene ring is attached to the beta carbon. And so you're thinking the reaction you know of where that happened had a double bond here, right? Okay. So let's think backwards then. If this is the bond that we're going to make, thinking backwards just to the previous step, I would have had something like this, where there's a metal here. We'll decide what that is in a minute. And then what would this part have looked like? You mentioned a double bond. So here. Okay. Good. That's an alpha-beta unsaturated carbonyl compound. We talked last time about how these are reactive both at the carbonyl carbon and at the beta carbon. So what we use here for our organometallic reagent is going to determine whether we attack here at carbonyl carbon or here at the beta carbon. Do you remember what kind of reagent I want to use to attack at the beta carbon? Go ahead. Cuprate, right? So let's put copper here. Copper comes with 2 of these alkyl groups, though only one is reactive. Okay, is that going to work? Yes. Okay. And how do we get the cuprate if we had to start with this alkyl halide? Well, we can make the organolithium reagent first, and then we add copper iodide, and that makes the cuprate. Okay, so that's just one example of using what you know about reactions, recognizing patterns, recognizing that this group was attached to the beta carbon, and then planning a synthesis or a series of reactions as a result. Again, keeping the reaction straight is going to help if you recognize the pattern of nucleophile attacking electrophile. But if you need to use flashcards to help you remember what the reagents do, I have some recommendations in the last lecture. You can look at those notes to see what I think would be effective. All right, anything more you want to ask or say about that? Okay, the last thing we need to do in chapter 20 is deal with a situation that happens actually a lot in the actual chemistry lab. So suppose that I want to use this alcohol starting material and I want to get the following tertiary alcohol as my product. We would normally look at this tertiary alcohol and this carbonyl carbon and say, okay, I probably wanted to use phenyllithium or phenylmagnesium bromide, the Grignard reagent or the organolithium reagent, and have that attack the carbonyl compound to make a new carbon-oxygen bond. And then afterwards, I would add water to protonate on the carbonyl oxygen. The challenge is that that approach does not work. And the reason for this is that my molecule has a group in it that is also reactive with my Grignard reagent, and that group is the alcohol. So remember, I told you that we were going to pretend like these organometallic reagents were basically carbanions. And carbanions are highly reactive, and they're both good nucleophiles and really strong bases. Remember, the conjugate acid of carbanions is in the 40s and 50s. So if these things see any protons that are acidic, they can react with them. So instead of doing what you want this reaction to do, your Grignard reagent that is a strong base is going to remove a proton from your alcohol. That gives you the corresponding alkoxide and benzene. So we just came up with a very expensive way to make benzene. And we didn't get the product that we want. And oh, by the way, when we, after this, add water, we just get back to the starting material. So this is chemically sort of knocking our head into the wall repeatedly. So we need a better strategy. We need something. We either need a reagent that can attack the carbonyl carbon in the presence of an OH group, or we need to do something to this OH group to temporarily mask the problematic functional group. And that strategy of masking a problematic functional group is called protecting group chemistry. And the goal of protecting group chemistry is to change the OH into something that doesn't have an acidic proton. But to be general, the protecting group masks the offending functional group. But putting it on must be fast and easy and high yielding. Then once it's on, it needs to be inert to the reaction you want to do. Can't interfere with the reaction of interest. And then fourth, when removing it has to also be fast, easy, and high yielding. The reason we want it to be fast and easy is because we're lazy. The reason we want it to be high yielding is because in a multi-step synthesis, especially a synthesis with many, many steps, taking a hit in yield early on is really painful and limits the amount of material that you can make. And when you're trying to make metric tons of some important pharmaceutical product, yield matters and affects your bottom line. Okay, so the idea of using a protecting group is, can I put something on that OH group that's not going to interfere with the reaction? There are many protecting groups. There's a whole book. There are books and books of protecting groups. We will only encounter a few in this class, but that'll be enough to give you the general strategy. The protecting group for alcohols that we're going to introduce today is called, protecting group for alcohols is called the Cylil Ether. Remember, ethers are an oxygen bonded to two carbons. A Cylil ether is an oxygen bonded to a carbon and a silicon. Silicon's from the same row of the periodic table as is, same column as carbon and has similar chemistry, though it's easier to break an oxygen-silicon bond than a carbon-oxygen bond. So let me show you the reagent we will use to make the Cylil ether. Here we have silicon, we have a tert butyl group, we have a methyl group, we have another methyl group, and then we have a leaving group, in this case chlorine. If this were carbon, this would be a tertiary alkyl halide. It's, I guess, a tertiary Cylil halide. So you would expect probably SN1 type chemistry. The leaving group chloro leaves, gives you a positive charge on silicon, and then that can be attacked by the alcohol as a nucleophile. We're not going to show the mechanism for this reaction. It will be enough to just draw the products and know how to use this reagent. The product replaces the silicon-chlorine bond with the silicon-oxygen bond. You will notice that the hydrogen, the proton that used to be on that oxygen, is nowhere to be seen. We got rid of it using a base called imidazole. The structure of imidazole, which you don't need to memorize, is this. The basic portion of these lone pairs on this ring nitrogen. So you can imagine chloro leaving to give you a Cylil cation. The oxygen attacks the Cylil cation, and then imidazole removes the proton to give you this Cylil Ether, where you no longer have an acidic proton on that oxygen. The Cylil Ether is inert to base. You can put it in the presence of a strong base, strong nucleophile, and nothing happens to it. So it satisfies our criteria of being inert to the reaction we want to do. And this reaction, which is often called a protection reaction, is fast and high yielding. One other thing is that chemists get tired of drawing protecting groups, so we abbreviate them. And so there's a little bit of acronym alphabet soup that could be a problem here. We can abbreviate this reagent, which is tert-butyl dimethyl chloride. We can abbreviate that as TBDMS chloride. And then once the protecting group's on, we can abbreviate that as TBDMS. You're welcome to draw it out if you want to. You're welcome to use the acronym. Just make sure you know what it means. Not in terms of memorizing the structure, but in terms of what it does as a protecting group. All right, questions so far? So now that you've got the Cylil Ether in place, now we can do the chemistry that we want to do. Now we can add the phenyl Grignard reagent and then in a second step add water. That will give us the tertiary alcohol, but we still have the protecting group to deal with. So we need a deprotection reaction. And the reaction that works for Cylil ethers involves fluoride ion. And then because this reaction often happens in organic solvent, you need some counter ion that will help the fluoride be soluble in organic solvent. And a common choice is this tetrabutyl ammonium ion. The butyl groups help the nitrogen be soluble in organic solvent. It's positively charged, and it takes the negatively charged fluoro group with it. Together, these are tetrabutyl ammonium fluoride, or TBAF. Again, acronyms. What likely happens here, because silicon fluorine bonds are stronger than silicon oxygen bonds, the fluoro replaces the oxygen. Probably the reactions has some amount of water in it, because once we remove that Cylil protecting group, the oxygen from our protected alcohol gets protonated to regenerate the alcohol. And again, this deprotection reaction is high yielding. So we were unable to go directly from our starting material to the desired product. Instead, we had to take a detour through a protecting group, then do the reaction of interest, then remove the protecting group. Okay, that's the general sort of strategy. Questions? So there are tons of Cylil Ether protecting groups. Some of them work better in different contexts. You don't need to worry about any of that. There are lots of other functional groups that might interfere with these kinds of reactions, like amines. We don't generally use Cylil ethers for amines. We'll introduce protecting groups for amines later on. You can imagine that in a complicated molecule, you might need to do a lot of protect, then deprotect, then protect again, then deprotect again. It can be somewhat cumbersome, and long-term that can diminish your yield and diminish your efficiency. So the really exciting new chemistry that comes out in a lot of cases involves reactions that you can do without protecting groups. And then us chemists go, ooh, that's kind of cool. All right. So with that, I think that's it for chapter 20. We're now going to move into chapter 21, which continues on with aldehydes and ketones, but we're going to use as our nucleophiles things that generally require acid catalysis. We're going to use weak nucleophiles that probably can't attack the carbonyl carbon directly. So let me show you some examples of this. The first is the simplest, though it's also the most pointless. If you put an aldehyde in water, you form some percentage of a product that looks like this. This is a gem diol because you have two OH groups on the same carbon. Gem comes from the Greek word for twins, Gemini, twin alcohols. We also often use geminal to describe, as an adjective, those diols are geminal to each other. But it's also called a hydrate because if you compare to the starting material, we've added a hydrogen and an OH group. So how does this happen? Water is our nucleophile, but it's probably unreasonable to propose water attacking the carbonyl carbon directly because the tetrahedral intermediate that you would get from that has a negatively charged oxygen, which should be way less stable, way more unstable. That was going to be funny, isn't it? Way less stable than the neutral oxygen that you started with. So probably we can't do that direct attack. Probably we need acid catalysis. And even in neutral water, it turns out there's enough hydronium present to catalyze this particular reaction. So I'm just going to show you what happens first. The lone pair electrons on the carbonyl oxygen, which are the most reactive electrons in the carbonyl, will remove a proton from the acid, and that will generate the what I'm going to draw here, which is called an oxonium ion. An oxonium ion is any cation that has a positive formal charge on oxygen. Okay, that protonating the carbonyl oxygen makes it more reactive. And you can tell that it's more reactive just by considering the reasonableness of this resonance structure where the positive charge is on carbon versus this resonance structure which can put a positive charge on carbon but has to put a negative charge on the oxygen. Just based on that comparison, you should see that once we protonate the carbonyl oxygen, we make it even more favorable for the carbonyl carbon to be electron poor. Alternatively, you can think that, well, Oxygen's more electronegative than carbon and should be pulling electron density toward itself, and even more so when that oxygen has a positive formal charge on it. In any case, protonating the carbonyl oxygen to get the oxonium ion makes it okay for water to be a nucleophile and to attack the carbonyl carbon. If you use the resonance structure on the left, you need another arrow to break the pi bond. If you use the resonance structure on the right, you only need one arrow. But either way, you can tell that this reaction is reasonable because you go from one positively charged oxygen to another positively charged oxygen. So thermodynamically, that should be okay. At this stage, to get to our hydrate product, all we need is for another molecule of water to act as a base and remove our proton. Notice that that regenerates the H3O plus that we consumed in the first step. So our acid is a catalyst, and that allows us to form the hydrate. Okay. So far what you're seeing is the whole point of this was just to show you if you use acid as a catalyst, you can use weaker nucleophiles to attack carbonyl compounds. As a matter of practicality, different, depending on how electron rich or poor the aldehyde is, this equilibrium constant between aldehyde and hydrate will change. If the aldehyde's more electron poor, more hydrate will form. I don't have any equilibrium constants or examples of aldehydes that form more versus less. If you compare this ketone versus this aldehyde, ketones are more electron rich than aldehydes because they have two alkyl groups instead of one. So you would expect the aldehyde to form a greater percentage of hydrate than the ketone. All right. So that's one example of something that can happen to carbonyls. Why are we doing this? Well, a lot of biology happens in water, and biology also happens to have a large number of carbonyl compounds. So being aware of what can happen when you have carbonyl compounds in water is a key part of understanding the biochemical reactions that keep us all alive. We're going to do now a related reaction where instead of using water as our nucleophile, we're going to use an alcohol. And this is going to help us get ready to understand the structure and the reactivity of sugars, carbohydrates. But before we do that, any questions about the hydrate mechanism? Yeah? Yeah, the aldehyde is more reactive than the ketone. And it's just, if you remember, the line of reasoning is this. sp2 hybridized carbons are more electronegative than sp3. So sp3 hybridized carbons can donate electron density into sp2 carbons. So there should be more electron donation from these two alkyl groups than from just one. And the more these alkyl groups are donating into the carbonyl carbon, the less electron poor that carbon's going to be. Okay, what else? Oh shoot, the iPad is down to 3%. I can't figure out why it's not charging at the same time it's plugged in. Oh. It says the battery is charged. Nevertheless, it says it's at 3%. Of course, it also says that it's Tuesday, January 9th at 9:41 a.m. As always, we can never get past that time. So hopefully this thing won't die on us. I think we're okay. I've been watching the charge tick down, and we lost 2% in the past 20 minutes. So I think we're good for the next half hour. We'll see. Maybe it's time to get a new iPad. I think this battery may be done. Okay, so the next thing we're going to do is to take an aldehyde or a ketone. Let's just stick with the aldehyde, and we're going to use as a nucleophile the the alcohol. We're going to use this as both our nucleophile and probably our solvent, which means that going into this reaction, understand that you've got probably a vast excess of alcohol. We're going to need a catalyst. The catalyst is an acid, but we're going to need one that's soluble in organic solvent. The acid of choice, I think you encountered in 351, para-toluene sulfonic acid, or just TSOH. This is basically an organic soluble sulfuric acid. But we're going to use this as our catalyst. It's only present in a small amount. The product from this reaction is going to, instead of be a hydrate, it's going to be a molecule, it's a gem diether. We're going to have two methoxy groups attached to the same carbon. And this functional group is called an acetal. And we'll talk more about it later, but you see similar functional groups in carbohydrates. And so understanding how these form is going to be useful to us later on as we consider carbohydrate structure. All right, so getting from starting material to products, it looks like we've basically added two alcohols in place of each of these carbon-oxygen bonds, pi and sigma respectively. So how are we going to do that? Well, let's use what we know about carbonyl chemistry to predict the mechanism. We have an acid present. The most reactive electrons in our carbonyl are the lone pair electrons on oxygen. So a reasonable first step is to protonate the carbonyl oxygen to get this oxonium ion. That's another reason that is a reasonable first step is simply that this neutral alcohol, which we want to use as our nucleophile, is not reactive enough to attack the carbonyl carbon directly. We have to protonate it first to make it more reactive, just like we did above in hydrate formation. And at that point, the neutral alcohol can attack. I will point out that each of the steps I'm going to show you are equilibria steps for this acetal formation. So we'll talk about something you can do a little bit to promote formation of the acetal product versus the starting material. But it's also useful to recognize at this stage that we could go backward simply by having the conjugate base of our acid remove the proton from the oxonium ion. But if instead we used alcohol, the methanol molecule, as our nucleophile, we have it attacking the pi star at the carbonyl carbon. That breaks the carbon-oxygen pi bond. And the product that we get looks like this. You can tell it's reasonable for the nucleophile to attack, the neutral nucleophile to attack a positively charged carbonyl compound because the product also has a positively charged oxygen. So thermodynamically that should work. All right. Now what do we do when we get a tetrahedral intermediate? We ask, are there any good leaving groups? Good enough for what used to be the carbonyl oxygen to kick them off. So here is our familiar tetrahedral intermediate. And as we look at it, we can see that yes, actually there is a good leaving group. It happens to be this positively charged oxygen, which could leave as a neutral alcohol. And it would be perfectly reasonable for these electrons to kick back down and kick off that leaving group, but that would just be the backward step. And that's not going to get us any closer to the product. If in the product we need this alcohol group to stick around, so we need to do something to it to prevent it from being a good leaving group anymore. And that's where the conjugate base of our acid comes in. We can actually remove the proton from the methanol oxygen, and that stops the methanol oxygen from being a good leaving group. So we're using acid-base chemistry here to change who the good leaving group is. Now, comparing where we are here versus our product, we have added one of the two methanol groups, but we have to add the other. And right now, we don't have any good leaving groups on that sp3 hybridized carbon. But we do have an acid, and the acid can protonate the OH group. During the first hour, a student asked, well, how do I know that the acid doesn't instead protonate the negative, I'm sorry, I'm going to start again. How do we know that the acid protonates the OH group instead of the methanol oxygen? And I said, sometimes the acid does protonate the methanol oxygen, and if that happened, we would just be going backwards to the previous step. That's why this is an equilibrium arrow. But if we protonate the OH group, that will convert the neutral OH group into a positively charged group that is now a good leaving group and can leave as neutral water. So it should be reasonable for the neutral oxygen on methanol to kick its electrons down and kick water off as a leaving group. When we do that, we get another oxonium ion, only this time the oxygen is positively charged because of the methanol carbon. Water was our leaving group there. Now, if water attacked that carbonyl carbon again, that would take us back to this previous intermediate. If instead we use another molecule of methanol as our nucleophile, that's going to make a new carbon-oxygen bond with a positive formal charge on what used to be the methanol oxygen. Of course, at this stage, we could have lone pair electrons kick down and kick off this leaving group. Or we could use the acid, the conjugate base of our acid, to remove the proton from that leaving group to convert it into not a good leaving group. And that would also regenerate our acid. All right. Yes?
At the step where you kick off the leaving group, the H2O,
yes.
and you have that double bond come down,
yeah.
Could you have your nucleophile actually come in instead to knock off that group, or is it not strong enough?
Good question. Could you do a SN2 style reaction here where the nucleophile comes in and attacks? That sounds reasonable, but the evidence is that that doesn't happen and that you do actually have this intermediate. In terms of why, I'm not sure what to tell you other than anything I would tell you would be hand waving. I think the idea is that the lone pairs on this oxygen actually help the leaving group to leave. And that's an intramolecular reaction, so that's faster than the nucleophile finding this molecule. Okay, what else? Yeah?
Going back to the beginning of the mechanism, why, in this case, do we need to protonate the oxygen first so that we can do the reaction?
Right, you got to protonate the oxygen first to do the reaction because methanol, neutral methanol, is not a strong enough nucleophile to attack directly. If it did, the intermediate would have a negative charge on an oxygen, and getting a negatively charged intermediate from a neutral nucleophile is kind of hard. Yes?
What would be the yield of this reaction?
What would be the yield of this reaction? Well, that depends on how you run the reaction, right? Because equilibrium means that you can go backwards and forwards. So let's talk about that briefly. Can you think of anything you might do if you wanted to promote product formation here? Yeah? Can you get rid of the water? Yeah, that's strategy. That's the most effective strategy here. If you remove water, then you promote product formation. And that's simply a Le Chatelier's principle kind of thing. If you remove one of the products, the reverse reaction slows way down, and that makes it so that your product accumulates. How do you remove water? There are multiple methods to do this. If you take the 353 lab, you will sometimes use a hygroscopic salt. That means a salt that absorbs water. You'll stir that at the bottom of your flask, and that will soak up the water that forms, and that will promote the reaction. Okay. Other questions? So somebody during the first hour asked, do you need to know this mechanism? And I said, well, twiddling my fingers in this nefarious and sinister way, yes, you do. Which is a clue that you might see this again under more stressful contexts, right? Okay. Usually when people ask, is this going to be on the test, I say, yes, everything I say is important. Right? I'm a professor. Obviously, I think everything I say is important. Yeah?
So, was the PTSOH 6 catalyst that we used?
Yes, we're just abbreviating. The question is the toluene sulfonic acid the catalyst that we used? Yes, we're just abbreviating that as HA.
So it's not a part of the mechanism itself, it's just like a catalyst that we use.
Well, we're using it in the mechanism. Yeah, this is the acid. We're using the conjugate base of our acid then again here. So it is part of the mechanism, only we're just abbreviating it because we get lazy drawing things. Yeah. What else? Okay. Yeah.
Is there like a practical use to making this?
Is there a practical reason
in the real life?
why you would make acetals? Yes. So the acetal itself is very stable to bases and nucleophiles. These two methoxy groups are terrible leaving groups, and they also don't have acidic protons on them. So it turns out you can actually use the acetal as a protecting group. If you have a carbonyl compound that you don't want to react with some nucleophile, you can quick make the acetal first and then do the reaction wherever else you need to do it. And breaking apart the acetal is also pretty easy, and I'll show you how to do that in just a second. Also, there's a practical aspect of this because when you go to make rock candy, where you ever done this, you put Caro syrup and some sugar or whatnot, and then you boil it, and then eventually it gets thicker and thicker and thicker, and then you pour it out and it solidifies. What you're doing there, once you caramelize sugar, among the many other things you're doing, is you're making a bunch of acetals, linking a bunch of sugars together, which we can talk about more later. All right. Other questions? Let's see, we're down to 2%, and we got 10 minutes left, so we're right on schedule. This is good. So removing acetals is going to happen under similar conditions. We're still going to use an acid. Remember, okay, yeah.
Do we have to use TSOH?
Do you have to use TSOH? No. Any acid will do. Only you can imagine not wanting to use an acid that's aqueous, or you wouldn't want to use like an acid in water because you need to remove water to make this reaction go forwards. So any organic acid will do. Sometimes people use acetic acid or vinegar, which you can have as organic soluble without water. Yeah?
Did you say this also works if you're using a ketone?
It also works if you're using a ketone. Yeah. Good. All right. So breaking the acetal apart. Why would you want to do this? Well, if we're going to use it at some point as a protecting group, then getting back to the starting ketone or aldehyde would be important. In terms of metabolism, if you want to take glycogen, which is a big, long, multi-polyacetal, and break it into glucose so you can actually start doing metabolism, you're going to have to break an acetal apart. So you can do this in the lab under acidic conditions. In this case, you can use any aqueous acid, but you're going to need to, you want it to be in water because you want to push the reaction instead of towards the acetal back towards the aldehyde, and then your alcohol, you have two alcohol molecules that leave as leaving groups, but we generally don't worry about them at that point. But this is how you break the acetal up, okay? Now, the mechanism for this is going to involve all of these same intermediates, but we're going to push the arrows backwards. What does that mean? Well, remember that in OChem, arrows simply tell you what bonds form and what bonds break. All right? So the first, if we've learned anything from this mechanism, the intermediate that has, on going back to the aldehyde, the intermediate that has to follow the acetal needs to be this one, where one of the acetal, methoxy groups is protonated. So I'm just going to draw that here. Okay. Now, how would I push arrows to get from here to here? What do I need to do? Give you a hint, we've got that acid catalyst that was also there. So how do I get from here to here? Go ahead.
The lone pairs on the oxygen would attack the hydrogen on the organic acid there?
Yep. Right. Lone pair electrons on the oxygen attack the proton on the acid. We break the bond between that proton and the other stuff on the acid. Notice how those arrows tell me exactly what happened. Oh, this is why there was confusion, because I didn't actually draw. Is that better? Yeah. Okay. Thank you. If I do that again, just tell me, okay? You're not going to offend me. My ego is already is strong enough to withstand such assaults. All right. So yes, and notice that the arrows tell us what happened and tell us what the intermediate should be. This arrow means we made this bond. This arrow means this bond broke, and we have a negative charge on the base. Oh my goodness. Would you look at that? I am very sorry. That should have been a methoxy group. I did a poor job of copying down this intermediate. And so now I'm, okay, I apologize for that. Anybody want to ask any questions about my stupidity? So my mom's brother, my uncle, was married to my aunt. This is a fun story, isn't it? Her name was Dinah, and she passed away last year. And at her funeral, I learned something about her that I didn't know. She used to talk about her grandchildren as though, she used to say some of them were on the dream team. And the dream team was not what you think. It's not the elite core of grandchildren. The dream team were the grandchildren that were easily distracted and somewhat absent-minded. And Dinah herself was on the dream team, and she knew it. She would start talking to you mid-conversation. She was already having a conversation with you in her brain, and she would just start in, and you'd have to try to catch up. But my wife Amber says I am definitely also a member of the dream team, and you have seen evidence of that today. I have 4 children. 2 of my sons are members of the dream team, and 2 are not. So it's actually interesting. If you're on the dream team, welcome to the club. It's a fun place to be. If you're not, you can laugh at all of us because we're funny. Sorry. Okay, so where are we going next? Let's go back to that acetal formation mechanism. We've just drawn how to form this intermediate. The previous intermediate is that oxonium ion. So let's draw that oxonium ion. And as you recall, we had methanol there and water there. How am I going to get, I think I've done that right. Oh, there we go. How do we get from this intermediate to this one? Go ahead.
The lone pair on the right association group will form double bonds and kick off that leaving group.
Great. So yeah, lone pair electrons on the neutral oxygen will kick down and kick off the methanol leaving group. Notice that this arrow tells you that you made a pi bond, and this arrow tells you that the electrons in this bond broke and the electrons left with this methanol. Okay, so if we go back up and were to see what the next intermediate is, it would look like this. So how do you think I get from here to here? Water attacks. You break the pi bond. This arrow tells you that you make this new oxygen-carbon bond. And this arrow tells you that you break this carbon-oxygen pi bond and lone pair electrons end up on the oxygen. Okay, so we've gone part of the way there. What I want you to do in the meantime is I want you to take it all the way back to the aldehyde. Okay? Sure, why not? That's a good enough place to end. We'll see you guys Wednesday.